So now we have to do a little analytic survey. The methods we are going to use are mostly spectral methods. Well, spectrum is now thought of in a very special way, namely as the spectrum of a self-adjoint operator. And general program consists in finding spectral methods which could reproduce the topological invariance. This is very well or largely understood in the case of compact manifolds, but it's far from being understood in the case of stratified spaces in a sense you have heard this morning already, and in a sense which we will make much more precise. So let me start with reviewing certain things which in principle you should already know, but it's always good to have a review. So let's look first at the case of Cn with its standard scalar product. And we take a matrix or an operator, I should prefer to say. That is the space of linear endomorphisms. And then we use the scalar product to create another operator which I call a dagger, as long as we are in the bounded case. So this is just the Riesz theorem. You consider this as a linear functional in X, and then you get it, you see that this is linearly dependent on Y. Everything okay. And we are, of course, mostly interested in the case that A is symmetric, which simply means that we have this, which makes life much easier. So we should note that the norm, so this Ax dot Ax, is bounded by a constant times the norm of X. This is very simple because these are matrices if you write it in a basis form. But the infimum here is called the norm of A. Let me call this the smallest possible constant. This is not so easy to describe, and this is one of the reasons why you are interested in the spectrum of A. What is the spectrum of A? This is not restricted to the symmetric case. Is the set of lambda in C such that A minus lambda, it's another endomorphism, is not invertible. What does it mean? Well, if it's not invertible, then it's also not injective. So we rather define the complement, which is C minus spec A, which is called the resolvent set. So this is the set of lambda such that A minus lambda is invertible. Which simply means that it is bijective. And this is equivalent, as we know, fortunately, to the fact that we look at those lambda, that the determinant of A minus lambda is not 0. And then the spectrum is the set where the determinant is 0, which is a polynomial. So since we are in C, we get as many elements in the spectrum, then called eigenvalues, as we have as the degree of A, and the degree of A is this capital N. So spec A is a sequence lambda j where these could coincide. This I don't write here. And we call Fa of lambda is the kernel of A minus lambda. And Pa of lambda is the orthogonal projection onto Fa of lambda. And then we can write Ax is equal to the sum over all lambda in the spectrum of A, lambda times the projection Pa of lambda applied to X. And this is the main reason why we do this, because then we have very simple equations for everything that commutes with A. You get a nice decomposition in terms of the eigenspaces. Yeah, and these must be finite dimensional. So we also define the dimension as this here. So that's the heart of the matter, and that's of course very simple. It's not so simple, of course, to compute these eigenvalues explicitly. In general, it's actually impossible, but you can approximate, and in nice cases, you can actually do it. Okay, now let's go to a Hilbert space separable. Hilbert space dim H by infinite. So Hilbert space has an orthonormal basis, which is not a basis in the usual sense, but a basis in the sense of convergence. Every vector x can be expanded in a countable basis if I require a separable. Otherwise, it's more complicated. So this means that we have a countable orthogonal basis. And I want it to be infinite, to leave this simple case. Then we can do largely the same, except we have now to look a little bit more carefully at lambda in the spectrum. So recall, if I know that A minus lambda is bijective, so it's injective and onto, then the inverse operator is automatically continuous. This is the, let's say, the closed graph theorem. For example, implies A minus lambda bijective is equivalent to A minus lambda inverse. Okay, not that it only exists, it's an element of L of H. It's a bounded operator. So then we have to be a little bit more careful. So, several cases. Whoops. So, if it's not surjective, then the image could be, I mean, this is one case. The image is not the whole space. And so what I'm interested in is to assuming that the image is not closed. The image is not a Hilbert space. Yes? Lambda in the spectrum. That means this is not bijective. This I should have written in this way, and then I said it, but not explicitly. This means A minus lambda is not bijective. Okay? Now I analyze this case. Not bijective. One case would be this is not a closed space. Could be closed, but not closed. Well, then there is no constant such that we have an equality of this kind. Okay. Since if I had a constant like this, it would follow immediately that this operator has closed image. Can you see this? So this is something you should think about. If you have such a lower bound, then on the complement of the kernel, this operator is invertible. And therefore, this is 1 over C is the norm of the inverse. Okay, but if this is not the case, then we have a sequence xn, norm of xn equal to 1, such that A minus lambda xn converges to 0. Okay? Second case, assume that the image is closed. But I'm saying lambda is not regular. Lambda is an element in the spectrum. If the image is closed, it cannot equal the whole space, because otherwise, by closed graph, we would have that A minus lambda is invertible. So that means the orthogonal complement is not equal to 0, but this here is the kernel. So this is all very simple, but if you never heard it, you may be surprised. But it's very, very simple. So that means the kernel is non-zero. But if the kernel is non-zero, then of course you can find such a sequence. Take one eigenvector and repeat it infinitely often. Yeah? It's not forbidden that these could all be the same. So call this here A, i.e., also something to think about. Lambda is in the spectrum if and only if, well, let me say A holds. There is such a sequence. And now a little exercise just to get used to these things here.
Sorry.
Yes.
What is A? What do you mean in brackets?
This is the name of this
Okay.
relation here. Sorry. This is always a reference. This was the first one. Okay, so call xn weakly convergent to 0, and then one would write xn, so you don't take the arrow but just half of it, if so you take the scalar product xn y and send this to 0, for all y in H. This holds for all y in H. Then I say it's weakly convergent to 0. But this does not always exist. So that's the exercise here. Characterize the lambda in spec A without such sequences. In fact, this is a very important splitting of the spectrum of any not only bounded operator in two parts. One is called the discrete spectrum and the other is called the essential. This we do a little later. But this is something you should know, because what we want is to obtain operators which behave very much like matrices. And unfortunately, we have to do, to get this simple case, we have to do some work. Okay, this should be enough for the moment. Now, what we have to do is to construct a space, a Hilbert space, where we will do our work. And so for now, let me make a general assumption. Let me call this GA1. So M, now there's a hard distinction between Professor Banagel, Marcus, and me, because I call the dimension always M, and he calls it N. Yeah? Please don't be confused. Is a compact and oriented manifold. Marcus made this assumption also, but of course not in general. But this is the nice class we want to study first. So what are the differential forms? I assume that most of you are familiar with this, so I make a sketch very much like this. So we have this manifold M, and then we have its cotangent bundle, the dual bundle to the tangent bundle. And then we can form the exterior algebra. And we can also remember that Hilbert spaces have to be complex in order to have a good spectral theory. So I tensor this with C over the reals. In other words, these are differential forms as usual, but they have complex coefficients, not just real coefficients. And I call this lambda m to abbreviate things. And of course, we have a grading. And these are the forms of degree j between 0 and m. And we should say what an element is here. So lambda p of m, j, contains an element alpha. Then alpha is a map of Tm to the power j, or maybe I write it for you, j factors, which goes to C, and this is a K linear map. But this is not a tensor product, but it's an exterior product. So we also want that it is alternating. So if you multiply a tangent vector in there by lambda, you can pull out the lambda. And if you interchange two vectors, then you change the sign. Okay, that's very simple. And now we look at the smooth sections, and for convenience, I call this space little lambda of m. So that's somehow good for memorizing it. And these are the smooth sections of M with values in the exterior algebra, complexified exterior algebra. So what are these? So if I take an element, maybe I call this alpha p, an element alpha here, then I need to, no, I don't want to introduce too much notation. So I put again the j here, because otherwise it's a little complicated. And then I take j vector fields. These guys here are in the smooth sections of the tangent bundle. And map this to the smooth functions. And I want the same conditions. It is k linear. Okay, k linear now is a little tricky because the constant could change from p to p to any other point. So I say k linear over c infinity of m. So if I multiply this by a smooth function, I can pull it out. So k linear over c infinity of m and alternating. That's all. All and simple. And of course, what we do with this is integration. So we can integrate m forms over m. So alpha goes to the integral over m of alpha, which I hope you know. This is why they were originally invented. And well, you just make a partition of unity, so you can multiply the differential forms by functions with compact support, and you take coordinates, go into Rn, and write the differential forms in coordinates, which give these mapping to Rm, let's say xi, and then you replace the integral by the normal Lebesgue integral in Rm. And then, of course, you have to show that it is invariant under changes of coordinates. This is the tricky point. What you need is that the determinant of the coordinate phi times pi inverse is positive. This is the condition of orientability. Otherwise, this will not work. So I don't say anything more. What we then want, so the most important geometric operator is the de Rham operator, which was actually known before, but de Rham fully exploited it. D, which maps lambda j of m to lambda j plus 1 of m. So let's see, this is D1. What I didn't say, but I tacitly believe that you know the wedge product. So that means lambda m is an algebra under the wedge product, which I do not describe in more detail unless you insist in the exercises. So then we could analyze what this is. So this is d alpha wedge beta plus epsilon times alpha. I explained this, d beta. This is a kind of derivation rule, a Leibniz type rule, except for this factor here, which takes care of the alternating. This is an endomorphism, and if I restrict it to lambda j of m, it's minus 1 to the j times the identity of lambda j of m. So this is fiber-wise. Yeah, and it's a smooth endomorphism, of course. So if this is a j form, all you have to do is minus 1 to the j here. That's clear. Yeah? And there's a third property, d3, extremely important. The square of d is equal to 0. This means this is a differential in the sense of topology. So if I say lambda m d is actually a differential algebra. And it has cohomology, which is defined formally by these properties. But let me very briefly give you the definition of D. Now this is maybe not so well known. If so, all the better. This is due to Paley. So take alpha in lambda j, and then compute d alpha. So this is a j plus 1 form, and sometimes I like to write here these curly brackets in order to indicate a linear dependence. Now, so I take, sorry, this is too early. So I have k plus 1 vector fields, which I should have. And then the formula is the following. I goes from 0 to k minus 1 to the I, xi, applied to, leave out the ith field, k, yeah, it's okay. K is okay. Yeah, this would be what you originally think it should be, because this is what you would have as the derivative in Rn. But there's a drawback here. If I multiply, say, this by phi, I pull the phi out and the phi gets differentiated. This is not allowed. Then it's not a differential form. It should be linear over C infinity of m. And this has to be rescued. And this is done like this. So we need the Lie bracket. Of course, now I have to leave out 2 vector fields. So this has the advantage to define the D once and for all. And then you derive the local representations. Okay? This is also now how do you proceed now? You give this formula and then you prove that you have these 3 properties, and then you prove that a map with these 3 properties, oh, sorry, there is one missing. We need, so to speak, the induction beginning. df is the sum df over dxi. No, df is the normal df is the usual df, which we define just using tm and tm star, yeah, the usual df, which can be written anyway in this form: df over dxi, dxi. So I write the indices upstairs. Don't be confused, but the physicists know this. Yeah, so this is, and now using this Paley formula, we can make a little exercise from 1 we get. Okay, first of all, we should write alpha in a given frame. Xi are local coordinates. Yeah, then we can apply this alpha to all linear combinations. This should be a K form as before. D dxi1, D dxik. All these combinations have to be used, and I abbreviate this by something like this here. And then this object, which is, this is easy to prove, such a form, at least locally, in a neighborhood of a point. And then the d alpha, of course, this is what you use if you have to compute something. It's just the sum over these i's, d over, and a sum over some other index we have not used now, d over dxj applied to the alpha, and now I write for this just d over dxi, dxj wedge dx, again this abbreviation. This is the formula you certainly all know. From this formula you prove this here, and this here, and this here. Okay? So then you are done. But of course, you have to work with this formula. And one thing you see immediately is that the Lie bracket of two coordinate vector fields is 0. So you are left with this one. Then you have to play with it. Very often, it is necessary to use not coordinates, but frames. And these are also frames, but we use orthonormal frames, local orthonormal frames, which is called a LONF. Yeah? If we use a metric, a Riemannian metric G. Okay. So this I should really call Riemannian metrics, but we can put it together with the other things. So then we take EI, orthonormal frame, local orthonormal frame. There are also things with double O. What might that be? Yes, these are the oriented orthonormal frames, which is sometimes neat, but not now. And the dual is written as EI, and then get local frames EI. I don't describe the set for lambda. I value means the number of components here. Yeah, which are useful because define scalar products on all lambda I m locally. Namely, I just say, of course can write any differential forms in components with respect to this. And then I'm saying if alpha is equal to 8i times ei, now not summed, then I have the norm of alpha squared is equal ai times ai squared equal ai squared. This is very convenient. So get a scalar product in this way. I mean, it's kind of implicit because you always have to, if you really want to compute it, you take a point, you construct a frame, and you compute the forms in this frame. But the interesting thing is that this helps us to describe a Hilbert space, because now I can define a scalar product which I call 0 for some reason, which you will see later. This is the integral of the scalar product just defined at the point P. Okay, this is only a function. Now we need something to integrate against, and this is the so-called volume form. And this is a perfect scalar product, and the volume form is fortunately very easy. Namely, it's just the product of these co-vectors if EI is a length, not a length, a length, so it's oriented. Then this is well defined, independent of the choice of frame. So we have a perfect Hilbert space. So we take our smooth forms and close them up abstractly, if you like, in this zero norm in order to get this Hilbert space, because lambda m is not a Hilbert space. Yeah, it's not complete. This is a nuisance, but of course the trick one uses is always to avoid these non-smooth elements by taking approximations and so on. This is very simple. Okay, so now I can make some room. So maybe the third part could be called. Now we have a Hilbert space, very good Hilbert space, and we have at least one operator, which, however, is not a server-joint operator. So this is something we have to study. But first of all, let's say Riemannian, just a very little taste of Riemannian geometry. It starts with the Levi-Civita connection. Does anybody not know what this is? That's good. Yeah. So, I mean, there's the famous Koszul formula, which I call it, put the G up here because it depends on the metric. So these are three vector fields. You take the scalar product in G at any point, and now you express this differently. And this is kind of difficult to remember. So what you should remember is that this is a thing in itself, that these two are symmetric. You can exchange them. So what you first need is x, y, z, and then you exchange y, x, d. But the next thing, the z, is different, so now you get z, x, y. And then, of course, you need also the Lie brackets, and you get a minus sign, but otherwise it's just what you had written before, just changing a few inessential symbols. And then, of course, here you have to change again, C, X, Y. Rather easy to memorize. And this is unique. Which is a rather remarkable theorem, metric and torsion-free connection on Tm. So this is called the fundamental theorem of Riemannian geometry, which you certainly have seen at some point. And metric means, let me call this 2, and torsion-free is 3. Then 2 means that x applied to y, z equals nabla gx applied to y, comma, z plus x nabla, y nabla gx applied to z. And torsion-free means that nabla x, y minus nabla y x minus nabla y xy is equal to 0. And if you know these two things, then you can build this formula relatively easily. Okay, so this is a fantastic instrument which we can use in order to describe D. Let's see, this is a lemma. So we take a local orthonormal frame, then it is extremely convenient once you have this, which is what the metric gives to you. Here we don't have any metric, yeah, on this side. This is all done except for the right lower part. So I would like to express D by a frame. And the beautiful formula you get is the following. This means the operation of wedge product. So W Ej applied to alpha is just Ej wedge alpha. So this is an endomorphism. And then you take nabla G Ej. This is a beautiful formula. Amazingly enough, most books don't contain it because the differential geometers don't like to work with orthonormal frames so much, it seems. But you will see how nice it is. How to prove it? Yeah, this we could make also a little exercise. So use the Pauli formula. Wasn't this one, I think, yeah? It's always dangerous to do this because after a while you don't remember which line was which, but you will be careful about this. Use 1, but this is not enough. And a trick. So this is something for our exercises. At P, any point P in M, we can find a frame EI with EI EJ at P equals 0. Ja. Wie bitte? Ah, ja, diesen Fehler mache ich immer. I don't know. Sorry. Of course. The nabla, this is true. For some reason I cannot remember this. But at least somebody has seen that. I mean, the nabla xy appears in the curvature, which is very similar, but then you have a nabla here, right? Sorry. But this is, of course, the right thing. So this you have to use. That means that in the Pauli formula, all these terms here, again, disappear if you put in the frame, but only at a point. Yeah? So you have to be careful that on the left-hand side you write something which does not depend on the frame. And this here does not depend on the frame. Can you see this? Yeah, you have to replace this frame by another one. So you get a unitary matrix coming in here, but also coming in here. And then it sums to the Dirac delta in the right places. So then you can make strange transformations which show you that you actually get this formula, which is extremely useful. For example, let me see, I should not forget anything important. Yeah, I forgot something, but I will add it. So now we could, for example, think of getting something like the transpose of D, something we might need. So what should I do? Then I put D alpha, comma, beta. This is the scalar product. Yeah. At some point P, and I would like to put it on the other side. Well, I use this formula, and then I have the wedge product here, and nabla G Ej alpha beta at the point P, which is promising because I have this metricity of the Levi-Civita in this very simple case, but this translates to all the other tensor product bundles. And I can compute, this is of course also an exercise, the adjoint of the W of the exterior multiplication. That is of course interior multiplication. So here the nabla G Ej remains, and here we get the interior multiplication by Ej. Now it's the vector, not the covector, beta at the point P. Interesting. So what do we get then? Then we use metricity and get Ej comes out, alpha Eij beta minus the nabla coming here. Alpha nabla G Ej I Ej beta at the point P. A formidable formula, but not so bad after all. Now, as I pointed out, the left-hand side, namely this here, is independent of the choice of the frame. Yeah? So I could choose a frame which the property assume that this here is 0 for all ij. This implies that also by the Cauchy formula for all ij. Okay? Now I look at this part here, and this is relatively easy to prove because nabla acts as a derivation on the tensor product that we get here. The left-hand side, d alpha beta of P equals sum j Ej. I mean, this is one of the differences between analysis and topology, that you have to write much more if you want to make a few things intelligible. So this is what we have here. This is not independent of the choice of frame, because this Ej will multiply any factor which comes out, will differentiate any factor which comes out here. So now I look at this. So this gives the interior multiplication of nabla Ej. So interior multiplication, nabla Ej beta plus Ej nabla Ej beta. And this would be 0 by our assumption, yeah? Because everything is at the point P minus this is 0, so what we have here is alpha Iej nabla Ej beta at the point P. But this is also, this is what we really hope. Yeah? So now we get a scalar product where the alpha is on the left side without anything, and here's something which looks very much like what we want. But this is a little nuisance. So, but now comes the big trick. This is the divergence of a certain vector field x at the point P minus the other thing here. Sorry, here's no, this I have incorporated, minus the sum here, or minus, let me put it this way, alpha sum j, or we met to plus here under here, Iej nabla G Ej b. So why is this a divergence? The divergence of a vector field is, by definition, nabla Ei wait a minute. What was it again? This is not that I confuse something again. Here I have this is this is nabla EI xi. So this is nabla EI of x EI. This is EI what do I do? This is something is wrong here. Okay. If I call this a vector field X, EJX minus, somehow I forgot this formula. So let's say I leave this to you for a moment. We can do it afterwards. And then now we integrate both sides. So we find d alpha comma beta equals the integral of the divergence of x. Now here I have to write the volume element P minus the integral or the scalar product, I could say alpha minus some j I ej nabla g ej beta. Okay, and this is Gauss' theorem that the integral of a divergence is equal to 0. This you know, I hope. Do you? This integral will be a d of something. If you compute correctly what this is, maybe we do this afterwards. So this integral is equal to 0, and now we get d alpha beta equal alpha minus some eij nabla g ej of beta. And this I call, for obvious reasons, the formal adjoint of d applied to beta. This is in general a rather complicated computation, especially if you do this with coordinates. It's almost impossible. But this way is relatively easy. And also this is easy if you write it correctly, because what you have to do is you add one term here which contains nabla ej, ei ej, or ej ej, which is equal to 0. And then you write it in this form, and this is invariantly defined. This is okay. And this is invariantly defined because the other side is in no differentiation happening here, and this is the solution of this little thing. But this helps us a lot. In order to define the differential operators, which are really the main actors. But I bypass something which is normally used in these calculations, but is by far not as explicit as this here, namely the star operator, the Hodge star operator. And I guess that you know this, therefore this is kind of an exercise. So define this operator, which is really denoted by a star, of lambda m to itself, pointwise. So actually we can do it at P. and then it would be called star p, by alpha which star, so alpha p star p beta p equals the scalar product of alpha p beta p times the volume form vol g at p for alpha beta in lambda j of m. Yeah, so it is so you see, to make this work, star has to map a j form to an m minus j form, otherwise it can't work. And then you can derive an explicit formula for star p in terms of a frame, dual frame EIP, star is an isometry. That's something to prove. Compute star star. So you might think that star is actually an involution, but this is only occasionally the case, not in general. And then, of course, you can do this computation by knowing that alpha beta then becomes the integral alpha wedge star beta. And then you can do the same, well, not the same, but similar calculation in terms of d, which expresses the operator d transpose, but as you will see, in a nasty form. There's a very complicated sign of -1, which you have to keep in mind, depending on the degree of the form where you apply this to. And the advantage of this formula is that you don't have to worry about this. Of course, if you do something concrete, you have to, but lots of calculations are much easier. Okay, this was the star operator. So everything which is not really familiar can be deepened in the exercise part. So since I take this here by the very definition, and I do it again, and then what I get is clearly D itself. The symmetric operator D equal D plus D transposed, which maps lambda m to itself. A very nice operator. Unfortunately, it does not respect the degree. Yeah, so it mixes degrees. If you have something starting with something of degree I, it goes to I plus 1 and I minus 1. So that's probably why, because some people don't like it. I mean, this operator does not even have a name in the literature. Yeah, so I call it historically correctly, I think, the de Rham-Hodge operator. But what people have used a lot is d squared, which is called the Laplacian, and this is probably much better known to you. And this is equal to d times d transposed plus d transposed times d. And this formula is used a lot, but not so much this one. Okay, what is d in our representation? This operator equals, in a frame, the wedge multiplication minus the interior multiplication times the Levi-Civita derivative in the direction of Ej. And this here looks intriguing, and therefore we call it the Clifford multiplication by, now we have to make a decision, so we take this vector. And this has interesting properties. So, and of course also an exercise, the most important property is the following. By this recipe, I can define the Clifford multiplication for any vector field. Yeah, and take the dual vector field. By the way, the metric defines an isomorphism from T to Tm star. This we know. And this is denoted as the musical isomorphisms invented by Marcel Berger, but it's rather nice. Yeah? So, but you should always think of a non-degenerate bilinear form as giving an isomorphism from a vector space to its dual. Yeah, then you can work with it much more conceptually than just thinking of this quadratic form itself and its changes of coordinates. Okay, so then we know what this is, and then we multiply, and then we take the other combination, and then we get, surprisingly enough, minus 2 times the scalar product of the two. And in particular, if I square it's minus norm of x squared. And so you can amuse yourself now by computing this square and getting the Laplacian, but this is kind of tricky. Since this is not a scalar Laplacian, this is a system of operators because we have matrix coefficients. Yeah, now comes the interesting question. I think that this question comes now. Or maybe I forgot something else. No. Not really. I mean, remember, the goal is to do spectral theory. And now we have an operator which is defined on a dense subspace in L2. Yeah, but not on all of L2. I mean, we have to differentiate. Yeah? So D maps lambda m, which is sitting in L2, to lambda m, which is still sitting in L2. And the question is, how do I make a decent operator out of this? Yeah, how can I do spectral theory with this object? Of course, I could say what an eigensection is in eigenspaces. I could hope that the whole L2 space decomposes into eigenspaces, but this would be ad hoc and not with any theory. So what is the theory? So the theory has two aspects. So I can So the norm in L2 now will be renamed as the 0 norm. And then, of course, we also need a 1 norm. So we put an alpha here. And we say what the 1 norm squared is. This is just the 0 norm, so the L2 norm squared, plus sum j from 1 to m. And then I take this section's nabla ej alpha squared 0 norm. Oh no, I didn't. So this is something like the L2 norm of the function plus the L2 norm of the first derivative, both squared. Yeah? And so this is also called the first Sobolev space. Of lambda 0, no, of lambda m in, or lambda mg, associated with these dense space, and I close it up under this norm. Yeah? So this is the closure. Closure is equal to the first Sobolev space. And then I have a nice Hilbert space. I can do this, and it is very easy to see that D becomes continuous. Then D extends to a bounded operator from diesen on this Sobolev space. I did not give it a name, right? So this is now complicated because I had the 0 space where I put the 2 here, and lambda 2 becomes lambda 0, 2. This is for the square, and this is for the number of derivatives. Don't be confused. So this operator I call d bar, and this is in fact a bounded operator from this space lambda 1, 2 to lambda 0, 2. This is good in a way, because now we have a perfect definition. Yeah, so we have functional analytically done something nice, but unfortunately for the spectral theory, it doesn't help us in the least, because spectral theory wants to analyze, I can remove this here, I think, the inverse of an operator in a single space. And so we changed the point of view a little bit and do the following. It's only a slight change, but it's quite nice. So here we have the space lambda 2, and here we have the space lambda 1, or lambda 0, lambda 1. This one is sitting here, and it's dense, because lambda is dense here and dense here, different norms. And so I could view the operator D as acting here. But then I should agree to drop the boundedness. Yeah, inside the space, the same Hilbert space, it is an unbounded operator, which is not defined on the whole space. Okay? So consider D as a densely defined closed operator, closed unbounded, sorry, closed comes later, in lambda 0, 2. So I cannot require that the operator is defined everywhere. So it's an unbounded operator. And it is closed. So what does this mean? This means that I look at the graph of the operator. What is the graph of D? Well, this is the pair, say, alpha D alpha, alpha in lambda n. This is the graph. And this sits in lambda 0, 2 times lambda 0, 2. This is the normal definition of a graph. Yeah, now I want to take the closure of this graph and I would like to have that this is the graph of an operator. And this is, of course, not necessary. You can easily make examples for such maps where you don't have this property. So this is also fairly simple algebra. And I make here another little exercise. Now these notions have to be used all the time. So call, maybe I put this here, a definition. A, not to mix it up with this, is closable in lambda 2 if and only if the graph of A closed equals graph of A closed for some linear operator. So then one has a lemma. Now I forgot how far I went. Let's say for safety it's 5. Lemma. The following are equivalent. Oh. Yes?
Can you repeat what you mean by closed? You wrote that and it is closed, i.e. the graph. So, i.e.
This is the graph, and this is the condition.
These closed.
Yeah. This is the condition for something closed. And closable means if you start just here, then there is a D bar so that this holds. Yeah. So now I need another definition, unfortunately, or fortunately. So you may have seen the notation D star instead of D dagger. Yeah, d dagger I reserve for bounded operators. But for unbounded operators, we have to work quite differently, because now the duality relation is a little bit more involved. So again, what we want is that, so this is the motivation. I cannot write it here either. Maybe I write it here. Again, I want ax y equal x. And now I write here a star y. But what is the problem? So these x are not running through all x in the Hilbert space, only in a certain dense subspace. So this will not be true for all y. Yeah? Because if it were, then the operator would be bounded. So you have to single out the y where you can do this. They form the domain of another unbounded operator, which we call a star. Yeah? And precisely we do it in the following way. A densely defined and now I call the abstract Hilbert space just H. So A has a domain. This is where it is defined. And the closure of the domain is equal to H. So then Y is in the domain of another unbounded operator, A star. This is equivalent to the following fact, that Ax comma y. Okay, now I have to be a little bit careful. So I want an estimate. This is bounded by a constant which depends on y times x norm for all x in the domain of A. This is equivalent to saying that this is actually equal to x comma y star for some y star y. Because it means that if you consider this as a linear functional in x, which it is, then it's bounded by the norm of x. So this functional is continuous on a dense subspace. So by continuity, I can extend this functional, only this functional, to all of the Hilbert space. And by Ries, I get this. And this here I call A star of y because it depends linearly on y, obviously. Okay, this is the simple step. And then we add here with this explanation, and y star equals A star of y. So this is once you know it, it's easy, but this inequality is how you prove what the domain of A star is. This is what you always have to use, so it's better to include this in the definition. Yeah, so this is. So the following are equivalent. Now I can really say it. A for a densely defined operator A is closable. B, you see, if I do this, I find a certain subspace where these y, which are form the domain of A star, lie. But nobody tells you that this subspace is dense. It could be anything. Yeah? So this is equivalent to dom A star is dense. This is a very nice thing, and in this case, you can say what the closure of A is, namely It's just A star star. You see, if you have a bounded operator, then A dagger dagger is A. But A star star is the closure of A. So we should be a little careful. Maybe, I mean, this dagger notation was invented by Feynman, and it's also a reason to follow it, but it's quite useful to distinguish this point. So, in that, there you have to think a little bit, but not too much. And then we can define what we really want, namely to say what a self-adjoint operator is. A is self-adjoint A star equals A star star equals the closure of A. So if A were closed already, then it would just A star equal A. Yeah? But if you only did what you normally have, densely defined and symmetric, then you have to write it in this way. And then there's the famous spectral theorem, which applies only to such operators and gives you a representation, well, which we will not use, therefore I write it without further explanation. Spectral theorem. There is a family of projections. A is A of lambda. So A, of course, self-adjoint. Which increases that means that the space where this projection projects on contains this space. This means monotonicity. Yeah? Or that this projection times this projection is this projection. Such that we can write, so A x y equal the integral over lambda times d e a of lambda applied to x comma y. So this is a projection valued Stieltjes integral, which is the way it is, and you can rather easily determine the domain from these properties. And what is more important, you can form functions of this operator by taking function f, put the function f here. Actually, for every Borel function, you get an operator. But this is much too general, and we will not use it. We use it only in the most simple case, to which we do not come now. But this is actually the last thing I wanted to do, so I make it the first thing I want to do tomorrow, which is also nice. And well, a little of this part, which I wanted to finish, will be left for tomorrow, but I think it is enough for today. Thank you. Are there some easy questions? So who is completely unfamiliar with this stuff? Only one? And you found it difficult?
It's not my area, so that's
Yeah. Yeah, but it's kind of indispensable to see the analytic approach. Yeah? I mean, it will not be, not much will be used, but you should see the framework, you know, that is all on safe grounds and you can operate with it. And so you know the other stuff to some extent. Yeah? No, that's okay. I mean, in physics, who is a physicist? You?
No.
I mean, this is well known, right?
Yes, more or less.
Yeah, but it's used. I mean, used as a calculus, right?
Yes, yes.
And this is, I mean, this is what you should aim at. It's not necessary to understand the deepest foundations of it, but you have to be sure I can use these formulas under these and these conditions, and then it's enough. I mean, it's a very nice building. This is von Neumann's theorem, which for the first time put quantum mechanics on a safe mathematical grounds. This is not a small achievement. One reason why I love to talk about this, because before that, the mathematicians were very disconcerted with this matter because they thought they are working with infinite matrices which cannot have finite eigenvalues. Yeah? They had a complete misunderstanding, and I mean, there was also work by Hilbert and Schmidt before that, but von Neumann made it completely clear what it meant. Yeah, and so you see this, the funny phenomena that there are certain measurable values. Measurable values depend the expectation value of a variable. Then you put x here and compute this integral. And if you have a gap in the spectrum, there's nothing. Yeah? So that was hard to explain. And you have discrete spectrum up to a threshold, and suddenly you get ionization and everything is there. All these phenomena are fantastically recorded. This was the reason to have this theory. And we still have to live with it, yeah? Even though, I mean, I think stratified spaces have string theoretical importance. Yeah? But this is probably not our common area of expertise, but it's true. I mean, if you look at these what they call branes, these are stratified spaces normally. They're not just smooth manifolds wrapping around something. Yeah? Therefore, this is relevant. Okay, but it is a good point to stop.
Can you say a few words about the integral? So you integrate over an arbitrary Hilbert space.
No, sorry. I mean, I'm integrate over lambda, which is a real variable. Right? And if this if this function would be smooth, sorry, yeah, I should have written this here. Then you just take the derivative and integrate with d lambda. But of course, you want to allow monotone functions, and then you have these delta jumps. And this is what the Stieltjes integral is for. Yeah, I mean, but lambda is just a real variable. I mean, you could wonder, so lambda should be a complex variable, but we know that for a self-adjoint operator, these values must be real, and therefore it's okay. And this is why self-adjoint operators are so important in physics, because we hardly ever get a complex value in our measurements. Yeah? Normally it's a real number. And also this needs to be explained, and therefore he had to develop this kind of theory, which was not so simple because it was unknown. They were all working with infinite matrices, and this is much more subtle. Yeah? I mean, then you have to really be careful because you don't see these norms, these nice Hilbert spaces behind it. More questions? No. Okay. Thank you. And we